Self-driving cars have this one massive blind spot. And I'm not talking about what's in their mirrors. It's the weather. Think about it. Heavy rain, dense fog, and especially a full-on blizzard can totally blind the cameras and LiDAR systems that these cars depend on. So, that's the big question, right? How in the world do you build a car that can see straight through a snowstorm? Well, the answer lies in this really revolutionary sensor. And trust me, what it can do is pretty incredible. Okay, just look at this. On the left, that's what a standard camera sees in heavy snow, basically a complete whiteout. You can't see a thing. But now look at the image on the right. That's the view from a 4D radar in the exact same blizzard. It's just mind-blowing. It cuts right through the storm and sees the other cars as clear as day. This really shows you the fundamental problem we're up against and introduces the powerful new sensor that's solving it. All right, so let's dive into this thing. This amazing piece of tech is called 4D radar, and it's basically what gives a self-driving system a fighting chance when the weather gets nasty. You can think of it as the car's all-weather superpower. So what exactly makes this radar 4D? I mean, what's the fourth dimension? Well, older radars could basically just tell you distance and direction, kind of like a 2D map. But this new tech adds two more absolutely critical layers of information. First, there's elevation, which tells you how tall an object is. And then there's Doppler, which measures its speed. When you put it all together, you get this incredibly rich four-dimensional picture of the world around the car. But there's always a catch, right? Having these superpowers is one thing, but actually being able to use it is a whole different ballgame. You see, the raw data that comes streaming out of a 4D radar sensor, it's not a nice, clean picture. Not at all. It's what engineers call a tensor, which is basically just a giant, messy block of data packed with noise, random clutter, and interference. To put it simply, it's a hot mess. And this image here really nails the problem. On the left, you've got that raw, noisy tensor we were just talking about. Yeah, it's dense with information, but it's also just full of static. The goal, the real challenge, is to somehow process that mess and turn it into the clean point cloud you see on the right, something an AI can actually make sense of. So the big question for the engineers becomes, how do you get rid of all that junk without accidentally throwing out the important stuff? The actual cars. So that brings us to the first big innovation here. It's a really clever algorithm designed specifically to cut through that wall of noise and pull out a clear signal. And it's called CCTP. Honestly, the best way to get what CCTP does is to think about tuning an old-school analog radio. You know how you have to turn that dial just right, filtering out all the crackle and static until, bam, you lock onto a perfectly clear station? That's exactly what CCTP is doing. It's just tuning out the static in the radar data to find the clear signal of the cars on the road. And it's this really smart two-step process. So first up, it applies a coarse-wide filter. Think of this as getting rid of the most obvious background static, just clears the air a bit. But then it comes in with a second, much smarter, more precise filter that hones in on the things that are likely to be real objects. And what's really cool is that the final output isn't just one clean data stream, but two of them. This gives the AI a much richer and way more reliable view of what's actually out there. Okay, so CCTP does a fantastic job cleaning up the signal. Awesome. But that just leads us to the next big hurdle. Remember that elevation dimension we talked about? The one that tells you how tall things are? Well, it's absolutely crucial for telling the difference between, say, a car you need to avoid and an overhead highway sign you can just drive under. But figuring out how to process all that height data efficiently, that's a whole other challenge. So the old way of handling this was, well, pretty clumsy, to be honest. To save on processing power, the system would just take all that rich 3D data and literally flatten it into a 2D bird's eye view map. I mean, all that critical height information, just gone. The new method, which is called vertical encoding, or V, is so much smarter. Instead of just throwing that data away, it intelligently zeroes in on the most important vertical features, like what's the highest point and what's the lowest point of an object. Think of it as finding the top and bottom of a car. What this VE algorithm is basically doing is teaching the AI to see height the way a human does, right? You and I don't need to process every single square inch of a car to understand its shape. We just notice the key outlines, the roof, the wheels, the hood. That's what VE does for the AI. It helps it grasp the true 3D shape of things without getting totally bogged down in every little detail. All right, let's recap. We've cleaned up the noisy data, and now we're cleverly preserving its 3D shape. We're doing great. But There's one final massive problem we have to solve: energy. Processing all of this incredibly complex information takes a ton of computational power, which means it uses a lot of energy. And when you're talking about an electric vehicle, literally every single watt counts for its driving range. And this is where, honestly, the most futuristic part of this whole thing comes into play. See, conventional AI, the kind we usually hear about, called ANNs, they're kind of like a giant office building where every single light is turned on 24/7. It's incredibly wasteful and power hungry. This new approach uses something called a spiking neural network, or SNN, and it's designed to work much more like our own brains, where our neurons only fire or spike when they actually have new information to deal with. It's a way more efficient, on-demand kind of system. So, just how much more efficient are we talking? Well, the difference is absolutely staggering. This new brain-inspired spiking AI cuts the energy needed for this task by a whopping 78%. Let that sink in. That's like getting the exact same amount of work done while turning off more than 3/4 of the lights in that building. This is a total game changer for efficiency, and it could have huge real-world implications for the driving range and even the cost of self-driving cars. Okay, so now let's put it all together. We have the CCTP algorithm filtering out the noise, we have the VE algorithm preserving the 3D shape, and we have the super efficient spiking neural network doing all the thinking. So when you combine all three, what kind of results do you actually get? Well, the numbers really do speak for themselves here. The original system was running at about 50.7% accuracy, and it was guzzling over 7 joules of energy for every single frame of data it processed. Now look at the new system, the spiking RTNH. It's actually a tiny bit more accurate, but get this, look at the energy use, just 1.58 joules. It's delivering better performance while using only about a fifth of the power. That's just incredible. And hey, this isn't just about abstract numbers on a chart. Here's what that looks like in the real world. That second column shows what the old model would predict. See that? In heavy snow, it sees a ghost car that isn't actually there. It's a false alarm caused by all that noise. But now, look at the prediction from the new spiking model. It correctly realizes that's just noise and ignores it. So it's not just way more efficient, it's actually smarter and more reliable too. So to wrap this all up, what have we really learned here? It's that this amazing combination of new hardware and some seriously brilliant software is tackling one of the biggest challenges in self-driving. You've got the 4D radar giving the car eyes that can see in any weather. You have CCTP acting like a high-tech noise filter. Then VE comes in to help the AI understand the world in 3D. And finally, the spiking neural networks do all the heavy lifting with incredible efficiency. It's the whole package. These kinds of breakthroughs are what's really pushing self-driving cars to be safer and more practical than we ever thought possible. And it really leaves us with a fascinating question to chew on. Now that our cars are finally learning to see, even in the worst weather imaginable, what do you think is the next great challenge they have to conquer on the road to full autonomy?